Okay, in this video we are going to talk about voltage. Voltage is, there we go. There's a lot of different definitions out there. None of them are wrong, but some of them I don't think really explain it except giving you terms that we define in voltage and other terms that we don't know. So let's try and do it this way. Voltage is the change in energy per charge between 2 points. So there's a lot there. First of all, it has to do with energy. Also has to do with what's carrying the energy. The charges are carrying the energy. And every time we're talking about voltage, we're comparing two different places. So the change in energy per charge between 2 points. There's a lot to that. So a 9-volt battery. A 9-volt battery has 2 points to it. It has the positive end, has the negative end. So basically what we're saying is if we connected wire between those ones or made a circuit between those 2 points, then for every, and it's a 9-volt battery, so it would be 9 volts or 9 joules per coulomb. That means when the charges leave one side of the battery, they'll have a certain amount of energy. For every coulomb of charge that takes this trip around to the other side, every coulomb of charge will have lost 9 joules of energy somewhere along that path. If we looked at a different one, like a 1.5 volt battery, which is a AAA, AA, C, and D batteries, well, the points aren't on the same point, but there is one point here, and then on the bottom is the other point, right? And if we connected a circuit, we connect a wire, we'll put a resistor in this one, not a very good one, but a resistor in this one. Every coulomb of charge that leaves this side of the battery will have lost 1.5 joules of energy before it gets to the other side, because a 1.5 volt battery is the same as a 1.5 joule per coulomb battery, right? So we said it a couple times, but just to make it clear, 1 volt equals 1 joule per coulomb. So if this is a 1.5 volt battery, it's 1.5 joules per coulomb. We don't know how much energy this battery is going to supply because we don't know how many coulombs of charge are going to leave. But we know for every coulomb of charge that does leave, it will drop off 1.5 joules for energy. Conservation of energy tells us can't be created or destroyed. So if the battery's supplying 1.5 joules, or if the battery's losing 1.5 joules for every coulomb of charge that leaves, something else in the circuit must be getting 1.5 joules for every coulomb of charge that flows through it. Right? Which brings us to our big law that is associated with just voltage, Kirchoff's voltage law. The sum of the voltages in any enclosed loop adds up to 0. Now, to do this law, to look at this law, we're not saying things drastically different than what we just said a second ago. It really comes right from understanding the definition. But one of the things that we need to do it mathematically is I like to say we need to put in our pluses and minuses. And to do that, we do have to understand current flow. So we are saying in all cases we have positive flow, which means we are assuming the charges are coming out of the positive side of the battery and they are traveling around the circuit and they are re-entering the negative side of the battery. So the charges are flowing this way. Now, many of you will probably realize that's wrong, but that's the way we do it, positive flow, and that's certainly something we'll talk about more in class. So the flow of the charges are going around like this. Once we understand the flow, we could put in our positive and negatives. That means that with respect to this resistor, this is where there was more energy, this is where there was less energy. This resistor, more energy, less energy, more energy, less energy. So we put those in. Now we can look at his statement. The sum of the voltages in any enclosed loop adds up to 0. So if I go around and I go through this loop like this, and let's just say for the sake of argument I started right, let's use a different color here, I started right here, then let me go around. So the first thing I hit is the plus of resistor 1. So the voltage of 1, or plus the voltage of 1. Then the next thing I hit is the plus of this one, plus the voltage of 2. And then the plus of 3, so plus the voltage of 3. And then I keep going around And the first thing I hit on the battery is the minus, so it's going to be minus the voltage of the battery. I think I'm coming off the screen, so let me rewrite it again down here. Voltage of 1 plus the voltage of 2 plus the voltage of 3, because the first thing I'm hitting on all of those three components is the plus side. Then I hit the minus of the battery minus the voltage of the battery, and that's got to equal 0. So that's the statement based on his law. Now, we said that voltage is the change in energy per charge between 2 points. So that's good. Let's go back and see if that makes sense for what we're saying here. Let's say that this battery was a 9-volt battery. So between one end of the battery and the other end of the battery, there is 9 joules of energy lost per coulomb. So between here and there, the charges lose, in this trip that they take around that I have in blue, they lose 9 joules of energy. Well, something else is going to receive that 9 joules of energy. What's going to receive it? Well, this is going to receive some of it, this is going to receive some of it, and this is going to receive the rest of it. The energy that's dropped off here, here, and here must add up to 9 joules for every coulomb that passes through. Well, that's no different than what this equation's saying. Whatever the battery's supplying, those 3 resistors are using. All right, so let's look at another example. Now for this one, we have multiple paths, right? So I can go around, well, sorry, first one, pluses and minuses. Charges, current flow is this way. So plus, minus, plus, minus, plus, minus. So this is how all the pluses and minuses have to be set up. Now let's pick a loop. Now I've got a choice here. I can go either way, but I've got to pick one. I can't just go through the middle because there's no path through the middle. And there is my loop. So it starts and finishes right there. And just for the sake of argument, I'm going to call this resistor 1, 2, 3, 4, 5, 6. There we go. So the first one is the plus the voltage of resistor 1. Then it's the plus again, plus the voltage of resistor 2. I don't go 3 or 4, so they don't go into this equation. But I did go through 5, and I hit the plus side of 5. And I hit the plus side of 6. And then when I get to the battery, again, I hit the minus side. I know it's the minus side because it's the shorter line. Minus 120 volts equals 0. Now that makes sense too. There's 120 joules of energy getting dropped off for every coulomb. So the coulomb that takes the path that's in blue has to lose 120 joules. This gets some, this gets some, this gets some, this gets some, and then it's all gone. They have to add up to what it is. All right, so I could do another path. I'm going to start from the same place. I don't have to start from the same place. I just like to start from the same place. But if I picked a different point, and even if I went the other direction, the equation wouldn't change. So if I did this one, I still go through voltage, still go through resistor 1, I still go through resistor 2, now I go through resistor 3, and I go through resistor 4. Negative side of the battery, this isn't looking drastically different than the other one, equals 0. So the charges that take the green path still have to lose 120 volts or 120 joules of energy for every coulomb that takes that trip. And the first 2 are the same ones, and then 3 and 4 are other ones. Now, those are the paths that charges would take. So those are the places where we lose 120 joules of energy per coulomb. But Kirchoff's law says any enclosed loop, and any becomes important here because I can pick another loop, and it doesn't have to be a path that a charge takes. But if I go back to this one and I pick a third path, pink, I pick a third path, and let's say I start here. Again, I don't have to start right there. Oh. And oh, that's not pink. Let me do it in a different color here. It does not want to change colors for me. There we go. and I go around, and let's say I do that. I start and finish here, so that's my loop. I go around, the first thing I hit is resistor 3, and it's the plus side, so it's plus the voltage of 3. Then I hit the plus side of 4, plus the voltage of 4. Then with 6, I don't hit the plus, I hit the minus side. So minus the voltage of 6, minus the voltage of 5. I'm back to the beginning, so that also has to add up to 0. Now that's not a path that a charge will take, but it still has to be right. These two voltages here have to add up to the sum of these two voltages here. Right? And now that makes sense, because if I look at my first two equations, well, they both have 1 in it, so that's got to be the same. They both have voltage 2, and those got to be the same. They both have 120, and they both equal 0, so all of that's the same. So it's kind of safe to say that 5 plus 6 has to equal 3 plus 4, which is just what this equation's saying. So it gives us some other information. Even if we go through loops that the charges that are passed that the charges don't take, it still tells us some similarities about voltages or some relationships with the voltages. All right, so now let's look at an even more complicated one than that. All right, so let's say this is one. Now this is a pretty complicated circuit. It's got 3 different power supplies. It's got 4 different resistors. We've got a lot of things that the charges could be doing. Now again, what we need to do is we need to assume a path. Now it's still coming out of the positive side going into the negative side. We might be wrong somewhere, but either way, the equations we make, even if we assumed a wrong direction of current, as long as we do it through that whole path, that's okay, because it'll just give us a sign issue later on. If we said that current was going this way and it was wrong, then we would get a negative voltage instead of a positive voltage. So let's just pick some directions for things. And even if the directions were wrong, it doesn't matter, because the equation still has to be right. So current comes out the positive flow. So that makes this positive. There we go. And this negative. And I'm going to say that current's coming out of this one too. So that's going to make this positive and this negative, which means all the current goes down, which means that makes this positive and negative, and that makes this positive and negative. So that's how I visualize the current flowing, and I think I'm pretty right on that. I could be wrong, because this one here could be changing things. We could have current flowing this way through this one, right? So I don't really know for sure if it's flowing down through this resistor or up through the resistor, but in the end it doesn't make a difference, because the math still has to work, because that's what negative numbers do for us. All right, so let's make some equations based on this. All right, so I'm going to pick a loop and I'm going to draw it. I'm going to start here. I'm going to go all the way around the outside. There we go. Plus the voltage sorry, let's number them too. Let's call that 1, 2, 3, 4, just so we have some things to work with. Okay, here we go. Plus the voltage of 1, because I hit the plus of that one, minus the voltage of 2, because I'm hitting the negative side of that one. Hitting the plus side of the battery there, so plus 10 volts. I'm hitting the plus side of the other battery, plus 30 volts. And then I'm hitting the minus side of the third battery, minus 20 volts, equals 0. So I could say voltage of 1 minus the voltage of 2 plus 20 volts equals 0. Or I could rewrite it another way. I could say the voltage of 2 equals V1 plus 20. Right? So there's a few different things I can do there. But that's the equation. I can do anything I want in the algebra. As long as it's right, I can do the algebra to rewrite it in different ways. All right, I'm going to pick a different loop, and there it is. I'm going to just stick around there, and there is a loop. Let's start and finish there. So still plus V1. Now plus V3 minus 20 volts equals 0. Now I'm going to go this way. Plus V2 plus V4 minus 10 volts equals 0. Let's see. I can go this way. Plus V4 plus 30 volts minus V3 equals 0. And I'm not sure. Yeah, I have a few other ones. I'm going to do one more just to show that we can use this in a lot of different ways. Bear with me. There we go. Let's use that color. Alright, so let's go this way. I'm going around and I'm going this way. And as I look at this one, right, there's a few I can make like this, but sorry, off the paper. And then there. Alright, so there we go. So what would that one be? Well, I'm hitting plus V1. Sorry. V1. And then I'm hitting that's V1 plus V4. I keep going, I hit the positive side of 30 volts. I keep going, I hit the negative side of the next one, so minus 20 volts. And I'm back to the beginning. It might come off the thing, but that has got to equal 0. So there's another example of how the voltage laws have to work. There are 1, 2, 3, 4, 5 equations there. I could have made more. Every single one of these equations are mathematically correct, and they all have to be proven true for the circuit. Okay, so there are some examples of what voltage is and how to apply the voltage law.